Okay, so as we're getting towards the end of this part of the chapter, really the core of what we've been working on here. So we just worked out how to get the variance for our sample of data, our raw scores 54321. And so now we're going to take the next step, the last step with this, again, turning that variance into standard deviation. So remember, if you've got variance and you want to turn it into standard deviation, you simply square root it. Now, I will mention that there's a lot of homework problems on and off throughout the text where the authors will write the problem where they will give you standard deviation, but you need the variance to go the other way. So remember, if we want to turn variance into standard deviation, get the square root. If you want to turn standard deviation back into variance, just square it. So that'll be a handy little thing to think about as you're looking at different homework problems in the book. They like to do that one a lot. When they know you need variance, they give you standard deviation instead. So either square it or square root it to move either direction. All right, so back to the problem we're working on. Standard deviation for the sample. So again, we need to start with a symbol, and you should probably be able to guess what it is by now. Lowercase s. Take the exponent off because standard deviation for a sample, it's the same definition as standard deviation for a population. It's the average distance of raw scores from the mean. So we no longer have squared distances, so we take the exponent off the symbol. So we want to take the squared values and square root them. So this is also identical, really, other than the symbols changing, what they look like. The sample side and population side, it's the same. So if we think about sums of squares, variance, and standard deviation as three calculations we've been working on, sums of squares is the same for either side, sample or population. We're going to see standard deviation is the same on either side, population or samples. It's only variance that has that little degrees of freedom change in it. So that means that this is basically the same formula as you would expect. Several different ways we could have written this one, but standard deviation is the square root of variance. So again, here I wrote it with a symbol, here I wrote it with a formula. Earlier I wrote it with little n minus 1, but that is what degrees of freedom is little n minus 1. So there's lots of different ways of writing it. Either way, what we had was a standard deviation of a variance of 2.5. So all we have to do is get the square root of 2.5. So get a calculator out of here. 2.5 square rooted is 1.58 on my calculator. Again, I think it was 1.41 when the data represented a population. Because we made that adjustment in variance, that degrees of freedom adjustment for the variance score inflated a little bit, again, to be a good estimate of the population, which means that as a result, of course, the standard deviation ends up inflated a little bit to be a good estimate of the population they came from. So those are our three major means of measuring variability in our data: range, variance, standard deviation. So now let's talk a little bit more about how to use this information, particularly standard deviation. Again, we're really focused on descriptive statistics at this point in the course, and as I previously mentioned, that means standard deviation. Variance is for inferential, typically. Standard deviation is for descriptive. So if we want to describe our data, paint a more complete, a little more refined picture, one of the things we really want to do is use both the standard deviation and the mean. And from here on out for this chapter, population samples is basically the same thing. So whether we want to describe a sample of scores or a population of scores, what we ought to do is use the mean and the standard deviation together. So one of the things that we looked at in an earlier clip for this chapter is this normal distribution. And again, we said most of the scores, the lion's share of scores, are going to be in this central hump. Remember, we got our frequency axis over here, so these are the more frequently occurring scores. These are more rare scores down here in the tails. Well, what we know, and you'll have to wait to chapter 6 to see how we know this, but what we know is that if we put a line here for the mean, and we sort of box this off, this sort of central area here comprises roughly, approximately 70% of all the scores in that data. So 7 out of 10 people are going to be somewhere inside of that shaded area. So what we can do is take the value for the mean and the value for the standard deviation and put it together to figure out what that is. So let's say, let me get a fresh one up here. Let's say that we have, we'll call it a population. I've got a population of scores that has a mean of 50 points and it has a standard deviation of, oh, let's just say 10 points. This would be a T-score scale, but you don't need to know that. So it tells us that the mean is 50 and that on average scores strayed 10 points away from that. So what that would tell us is that in a curve like this, 50 points is here in the middle, and if we just sort of box off that middle section, this 70% zone, that if we go down 10 points to 40 and up 10 points to 60, why did we go 10 points? Because the standard deviation is 10 points. That 70% of the scores live somewhere between 40 and 60 points. There are certainly scores lower than 40 and scores higher than 60, but most, again, approximately 70% of all the data is between 40 and 60. So we have some measure where the mean is 50 points and the standard deviation is 10 points, and we say, oh, well, let's look at Sarah's score. And Sarah has a raw score of 45 points. Now let's think, at the very top of this chapter, I said that there were kind of two goals or missions for measures of variability, and that second one is the one we're dealing with here. How well does this one score represent the whole distribution? Well, they've got a raw score of 45. Where would that sit in this? Oh, well, a 45 is right here. So is it below the mean? Yeah, it's below the mean, but if we think about this range as the common range of scores, where the typical people are, where the typical scores are, is this score a typical, a socially common score? Yeah, absolutely, because most people score between 40 and 60, and so did our hypothetical Sarah. So we can start to describe individual scores relative to the entire data set. Again, our second purpose for variability. Some other person, say I had a Sarah, so now we'll have a Sam. Sam got a raw score of 35 points. Well, how does he compare to the rest of the class? Would we say that his performance was average or common, typical? Or would we say it's above average? Or we say it's below average? Well, a 35 is going to be, here-ish. The typical range of scores is still between 40 and 60. So how did Sam do? He scored below average, not just below the mean. He scored below the average range. He scored lower than most people, if you will. Now beware, don't always take lower as worse, right? Sometimes a lower score is better. If we're measuring depression, a lower score would tend to be a healthier person, right? So let's not get judgments, qualitative judgments wrapped up in that. But the idea here is that we are absolutely taking a score and evaluating it. We're getting further description of, is this a good performance, an average performance, a below average performance? Further description. So you take the mean, go up by the standard deviation, down by the standard deviation. Everything in between is common or average. Everything outside of that is above or below. There are ways of being more precise, more fine-tooth and cutting out all that out, but it's sort of a rough description. Okay, on we go.